All right, for this problem here or this review, I just want to go over forces all together. And forces, I think most kids can intuitively understand forces pretty easily as long as you keep drawing the pictures. So I'm going to give you a couple scenarios. The first scenario is just a box on the ground. Let me draw this a little more clean. Box on the ground, and let's just say someone is pushing that box and it's traveling at constant velocity. All right, if an object is at rest, let me rewrite this. An object is balanced if it's at rest or it's traveling at constant velocity. So I see this, okay, this object is balanced because it's traveling at constant velocity. Let me draw a system schema. Your system schema, this is the bubble diagram. This would be the person's involved, the box is involved, the floor is involved, and the earth. Just to clarify, floor and earth are different objects. The earth, think of it as just like the metal sphere that has so much mass it pulls you down. The floor just happens to be what is underneath you at that moment, like whatever particles are right there. FG goes to all these objects. The person's on the floor and there needs to be friction for them to move. So they still interact. The person pushes a force into the box, and the box also interacts with the floor the same way the person does, basically. All right, so this is my system schema. I see 4 forces. Let me draw whatever forces are on this box. So we have FG. We have F, in this case, that would be force applied, force normal, force applied, and then force friction opposing the motion. This is my force diagram. So this first one I'll write over here just so we're all clear. This was a system schema, the bubble diagram. We got these force diagrams here, and let's draw the VAD. I notice, hey, it goes back to 0. There is no F net here. F net is equal to 0 newtons. And that's another trait of balance forces. F net's equal to 0. All right, very good. Well, let's do the same thing, but instead the guy's pushing the box. So we're gonna do the same scenario. Guy's pushing the box, but instead of it being constant velocity, we're gonna say it's speeding up. So speeding up to the right. All right, well, that brings us to what is unbalanced. So I'm going to kind of separate it here. Unbalanced, you have a couple things it could be. An object could be speeding up. It could be slowing down. Or it could just be changing directions. All of these, changing directions, all of these are it's accelerating. And I know that F net is equal to ma. That's Newton's second law, and that's very important with unbalanced. In balanced forces, acceleration was 0, so F net's 0. In unbalanced, it is accelerating, thus F net has to be some value. Okay, so I have like these scenarios. I know I'm speeding up to the right now. So I think I still have all my forces there, and I think all of them should still be the same, except I think the one thing that might change is going to be my applied force. I think the only thing I'm going to change is the applied force, and I'll make it very big. And so when I draw my VAD, FG, I go with FA, FN, and then I go FF. I don't know the numbers. I'm just kind of making this stuff up, but I want to emphasize, hey, I am speeding up to the right. If like this part canceled out with this part, I'm left with still this much FA, and I have this gap here. I'm left with an F net. What is F net? F net is I add up all these forces and they end up one way or the other. Whatever's left over is my F net. And so FG and FN had canceled each other out, so I was only looking at, this F net's just equal to FA minus, this should have been force friction, minus force friction. It's also equal to MA. All right, so this is a good example of unbalance. If let's say the person stops pushing it. Well, the person stopped pushing the box. So one more scenario, I would take out force applied. That takes out this. So my vector addition diagram looks like this now. FG, FF, and FN. I could see, oh, well, my net force is just whatever my force friction is. F net's just equal to force friction. It's the same direction in everything. And that would be equal to whatever its mass times acceleration is. So I think most kids at this point, I think, are understanding kind of these concepts. Draw the diagrams. Draw the system schemas, the force diagrams, the unbalanced forces, even if they don't necessarily make you. A lot of times that solves problems. The only thing I'm going to mention also is Newton's third law. Every action has an equal and opposite reaction. Every action has an equal and opposite reaction. If the box is being pushed up by the floor with force normal, the box also pushes back down into the floor. One thing I just want to point out, Newton's third law problems, you cannot find the Newton's third law pair in one force diagram. You can find it in a system schema. So in a system schema, this is the Newton's third law pair. I want to be very clear. The gravity, the weight of the box, which is Fg, this here is not a Newton's third law pair with Fn. Even if they have the same values, they are still not Newton's third law pairs with each other. The Newton's third law pair between the box's weight is with the Earth's weight according to the box. All right. I think this is all I have for y'all. Please do the midterm review. I'm going to send out a completed solutions version of the midterm packet so y'all can go over just in case you miss it in class or something. And good luck. I know you guys can do great. And I expect you guys to do really well because you've done well the whole year. Thank you.